Hello. Little extra knowledge for you. Sometimes people jump over some of the history in math. I think in this case it's really neat, and so not on any test, but I wanted to take just 5 minutes to just talk about some of the history behind the ideas of limits and calculus. I'm not even going to come close to doing this justice, but I just want to be able to point in the different directions so you realize how broad and long this is. I have a lot of respect for Isaac Newton as well as Leibniz, who you'll hear their names a lot when you first learn calculus, but I think it's really important to understand that while they contributed a lot, that this is really hundreds, if not thousands of years of people deeply thinking, sharing ideas, and working with each other from across the world to get to the point where you could learn calculus in a quarter or two or three. Granted, maybe some pre-calculus classes, but this used to be only a couple people on the planet, and now you're one of, well, many, still a very smart math person, I'm sure. But we can really trace back some of the earliest questions that we have written down to ancient Egypt. And part of that is just because they were good at writing things down. Also, they were really good at math. So this was a couple thousand years ago. Hard to know the exact date, but probably around 4,000 years ago, we have early recordings of actually like math problems. And some of the problems in there show that they were tackling questions of area of curved objects, which we now understand as really the dominion of calculus and limits. And they even had a surprisingly good estimate for pi in order to do this. So hard to know exactly what was on their brains at the time because we have so little knowledge of the methods they were doing. But certainly tackling similar problems, 4,000 or 5,000 years ago in ancient Egypt, those people were on the ball. One topic that maybe you've heard of before is this fella Archimedes. He wasn't even the first in ancient Greece, but I wanted to bring him up because his name is often familiar. He was one of these guys who was trying to figure out things like the area of a circle in particular by filling it up with other shapes, bigger and bigger shapes or smaller and smaller shapes, which to us feels a lot like a limit. And for ancient Greece, they would call it the method of exhaustion, and started applying basic ideas of finding limits or finding areas using smaller and smaller airs or closer and closer approximating shapes. And they didn't quite have the language to formalize it. And in fact, formalization wasn't quite clear what formalization would be back then. Something else we often take for granted. So that was 287 BC was when he was born, and he wasn't even the first in ancient Greece to be doing these things. Meanwhile, I don't know if this is meanwhile, but actually this would be later. Someone else we often give a lot of credit to is Alhazen. Forgive me if I pronounced that a little bit wrong. He was using degree 4 polynomials to find volumes of 3D shapes like paraboloids, and he made a big contribution there. I'm going to jump over ahead to Madhava, who I probably also said the name wrong, and sorry, this is the best picture I could find. And all of a sudden, he and his entire school were doing things that look a lot like infinite series. And the way that we understand infinite series is also with limits. If you ever look up and you say, oh yeah, it looks like in India they had 30 digits of pi well before anyone else. It's because of this guy and actually his entire group of people around him and their ability to work with things that we would now call, Taylor series, and using methods that look a whole heck of a lot like taking a derivative. So this was 14th century over in India. Point being, both that this was being worked on all over the world, but also independently, lots of different cultures were realizing that these problems were important, and that the methods to do them involved something looking like infinites and infinitesimals. In fact, the notion of infinitesimal got people into a lot of trouble because we weren't really sure if that was a rigorous idea. And even when we got to Isaac Newton and Leibniz, they were still talking about infinitesimals, and there were still a lot of mathematicians arguing like, that's not real, that doesn't make any sense, we shouldn't be trusting this idea. Much later, back in the 1700s, Isaac Newton and Leibniz, at about the same time, in different countries, were inventing their versions of calculus. Isaac Newton tended to be a lot more physics-based. He tends to be a lot harder to understand if you read his notation. Leibniz Most of the notation we use today is because of him. He thought a lot about what is the cleanest way of writing something. He had a lot fewer applications to, say, the realm of physics than Newton did. But there was a big debate over who invented it first. Did one of them steal it from the other? My quick take is probably not. They probably were just working on something that was important to everyone at the time. But because of this, there's a big feud between English mathematicians and continental European mathematicians, partially because the war over who invented it was as much about national pride as it was about any one of them caring as much. And so there were a lot of rifts between the two groups of mathematicians. Leibniz was, I should look this up. German? Austrian? I'll look it up later. You should look it up. But this really solidified calculus, and it was also taking place at a time where we had things like printing presses, so we could get this material out to the world. With that said, still a lot of disparate ideas, and someone who doesn't get enough credit is this person to the right, Maria Agnesi, who chances are, if you did anything like understanding calculus in the late 1700s, early 1800s, it was actually because of her. She was the first person to write down a book that would look anything like the books we have that had something like Calculus 1 and Calculus 2 in it. It also had some other ideas from geometry in it. But often credited as the first person to write this stuff down in a way that someone could understand, and also managed to make the connections between a lot of different areas and synthesize it into what was really important. So her contribution is, maybe it's because I'm a teacher, but I feel like we often overlook these kinds of contributions, which is what actually makes ideas flourish. But still at this time, we are still arguing about what on earth is infinite and infinitesimal. I realize in your brain you might still be arguing about that too, and that's good and healthy. But it wasn't until these two fellas, Cauchy and Weierstrass. Cauchy is a giant. Cauchy was on German money. So imagine being so good at math that you are held in the same esteem as we hold Benjamin Franklin or Alexander Hamilton to get on to money. And so Cauchy really wrote down a lot of formalities. He's responsible for a lot of imaginary and complex analysis too. The first ideas of how do you think about continuity formally was Cauchy. And Weierstrass, also a giant, he really laid down and connected all of these ideas of, okay, we can avoid all of these sequences by really talking about limits and writing everything in terms of limits. And so it's because of that we can talk about calculus without having a giant philosophy class about what is an infinitesimal and a big debate about that. All of these people were giants, and I'm skipping so many. It's definitely a disservice that I don't see anyone from say China in here. They had contributions as well, but it was easier for me to sort of draw in my mind a nice smooth connection between this clump of people. You can easily look up like Babylonian tablets from way back when that if you read between the lines you think, hey, were they doing something like calculus there? What kind of trigonometry was behind that? So point being, me and other people are going to talk a lot or mention Isaac Newton or Leibniz, and they were great people. But one of the ways you can tell that calculus is really fundamental and important is that people have been thinking about related questions to this since math has been around, and independently across a lot of different countries and cultures. And that the only way that we've gotten to where we are isn't because one person said, here is a calculus book, but because there were generations and generations of refinements and arguments and realizations of nice ways of writing things that are still honestly happening. People still argue about the best way to think about simple calculus ideas, and you don't have to rephrase questions that much in calculus to get to problems that we still don't know answers to. So it is both a long legacy, it is a broad legacy, and it is still a living and thriving legacy. I just thought it was worth taking a moment to sort of open that up and try to contextualize this a little bit. I'm sure I'll go on a number of rambling contextual rants in class as well. So hopefully that was worth your time. None of this will be on any tests, just for your enlightenment. Have a good day.